This is summary notes on Chapter 8, the gas laws. This video is about Dalton's law of partial pressures, and we'll see a health application near the end. All right, Dalton's law of partial pressures is an additive law. It involves mixtures of gases within the same container, and basically you're adding up the pressures to find P total. All right, so you're seeing the formula right here, where the total pressure is equal to the individual partial pressures. Okay, and that's basically it. It's probably the simplest of the gas laws that we've looked at in this chapter. I think the best example of a mixture of gases comes from our own atmosphere. So you see the partial pressures of the gases in our atmosphere here in this column. And let's get a wider swath for our highlighter here. All right. So we know that most of the gas in our atmosphere is 78.2% nitrogen, 21% oxygen. Those numbers are probably familiar to you, but you might not have seen them in terms of their partial pressures. All right, so the partial pressures are listed there for you. The remainder of the minor gases that make up the atmosphere is about 6 millimeters of mercury, less than 1%, for a total of 760. All right, so that's an interesting example from our real world. All right, now let's take a look at a visual that's more like what happens in industries where they have to store mixtures of gases or make up mixtures of gases to suit the different vendors that are out there. Okay, so we have a couple of canisters here. One has helium in it, the other has argon in it. They're the same size canisters, but you can see on the gauge we have 2 atmospheres for helium, 4 atmospheres for the argon. So if those 2 gases are placed together in the same canister, well, since the volume is the same, now they will now exert 6 atmospheres of pressure. Okay? So sometimes the challenge is to make sure all your pressure units are the same in order to work your problem. All right, so here's a problem. It says a scuba tank has oxygen in it. All right, so oxygen's pressure is equal to 0.450 atmospheres. And we have some helium, but notice it's at 855 millimeters of mercury. All right, so let's see what they want us to change things to. I said, what is the total pressure in millimeters of mercury? All right, if that's the case, I need to change my oxygen to millimeters of mercury. And I can do that by using that relationship, 760 over 1 atmosphere. Way back in the first video, we went through pressure units. Okay, so we do 0.450, or just 0.45 times 760 to get the pressure in millimeters of mercury. It looks like it's 342. Let's just move this over instead. All right, so now I can add these 2 together to get my P total. So P total is going to be equal to 342 of oxygen plus 855 millimeters of mercury of my helium. All right, well, I already have the 342 on the calculator display, so I just need to add the 855, or you can probably just as easily add them together without having to use the calculator. All right, so our grand total is 1,197, but we know we're going to need to adjust to the correct number of significant figures. And when I do that, this is going to round to 3 significant figures, and that will be 1200. So if I do that, I'll have to change it to scientific notation so I can show 3. All right, and that's my P total. Okay? That's it. All right. So try this next one. All right, I'll pause your video, give that one a try, and then come back and check your answer. Okay, so this problem this problem was looking for a partial pressure. They gave you a P total. I hope you caught that. The P total was 8 atmospheres. They gave you 1,280 millimeters of mercury for the partial pressure of oxygen, and we needed to find the partial pressure of the helium. All right, since the responses to the left were all in millimeters of mercury, that was your clue to go ahead and find the 8 atmospheres in terms of millimeters of mercury. And that's what I did over here on the side. Took my 8 atmospheres times 760 over 1 to get the 6080 or 6,080 millimeters of mercury as my P total. Okay. And then I can subtract the 1280 from both sides to clear that term. So I have my 680 minus 1280, and that will give me my partial pressure for the helium, and that turned out to be 4,800 millimeters of mercury. All right, you could just have easily have, if this wasn't over here, the answers weren't over here for you, you could have just as easily converted the 1280 millimeters of mercury back to atmospheres. And that's what I did here. Okay. So I divided 760 into 1280 to get my 1.68 atmospheres and subtracted that from 8. And that gave me 6.32 atmospheres of helium. So if you want to check and see if that checks out to be the same, we can certainly multiply that by the 760 millimeters of mercury over 1 ATM, and you do get that same answer. Okay? So don't believe me, give it a try so you can tell that. All right, the very last thing is just a conceptual topic, all right, that has to do with your heart and breathing. All right, so the partial pressures of carbon dioxide and oxygen are part of the breathing process. And it's just very interesting that there's so many people out there that have been suffering from COVID, and if they've gone to the hospital, the oxygen level is so important on making sure someone survives their episodes of being in the hospital. We always want our partial oxygen levels to be above 95% in the blood. Okay, so that's what they look for. My own granddaughter was in the hospital for a different respiratory illness, and they had her hooked up to an oxygen monitor. And we want 100% in our lungs. So you see that here in the diagram where the alveoli is. And I'm going to do my highlighter in the yellow. It goes through the heart, the arterial blood, down into the tissues. All right, in the tissues, oxygen is constantly being metabolized. The oxygen is constantly being metabolized and creating carbon dioxide. So oxygen is always depleting and carbon dioxide is always building. And as that carbon dioxide builds, it goes back into the venous blood, back to the lungs, so it can be exhaled. All right, so the partial pressure of oxygen is high in the lungs, which pushes it into the tissues because the concentration is low there. And as the oxygen changes to carbon dioxide, the pressure increases there. And since it's lower in the lungs, it gets removed to the lungs to breathe out. All right, so inspiration is when you inhale and you're breathing in the oxygen. Expiration is when you are expelling the air and you are releasing carbon dioxide back to the atmosphere. Okay, so that's a little health application for Dalton's law of partial pressures. And just remember that Dalton's law of partial pressure can be part of the ideal gas law as well, where you're looking at different types of gases that make up a mixture. So this can actually be expanded to include even more complex problems rather than just this additive type that we've seen in this video. All right, but we're done. And that is this chapter on gas laws.